Good morning, everyone. I'm delighted to welcome you back to our second day of the Genome BC Annual Genomics Forum 2024. My name is Federica Di Palma. I'm the Chief Scientific Officer and Vice President of Research and Innovation at Genome BC. Before we proceed today, I would like to just take a moment to acknowledge that here at Genome BC, we are gathered on the traditional, ancestral, and unceded territories of the Coast Salish people, the Musqueam, Squamish, and Tsleil-Waututh First Nation. And we do honor and respect the enduring connection to these people and what they have to their lands, and we are grateful for the opportunity to meet here today and broadcast this forum for you. Throughout the day today, we will investigate the role of genome engineering in promoting sustainability and environmental conservation. We will talk about clean energy solutions, sustainable bioproducts, and we will explore how genomic innovation are shaping a greener and more sustainable future. We'll also have the chance to hear about genome engineering and its role and efforts in species conservations, which offer a little bit of a hope for our endangered species and our ecosystems at risks. So hopefully throughout the day, we will explore all of this topic with a positive attitude and somewhat of a hope for the future and a thoughtful and responsible attitude to innovate while we safeguard our environment for the future generations. Before we move on to today's program, it is my absolute pleasure to introduce you our keynote for the day. But before I do that, I just want to remind you that you can ask a question at any time throughout the talk of the keynote. You should use the Q&A panel on the side of your screen, and we will do our best to answer as many questions as we can. So it is with great pleasure that I introduce to you Professor Orlando Rojas. He is the Canada Excellent Chair in Bioproducts at UBC and the Director of the Bioproducts Institute. And I had the greatest pleasure to meet Professor Rojas and to visit the Bioproducts Institute. And if you haven't done so and you are local, please do, because it's just quite special. In his role, Orlando synergizes an ecosystem that conducts multidisciplinary research to generate fundamental knowledge, but also translate that knowledge into application from seeds to cutting-edge biorefining technologies. Professor Rojas has many distinctions. His career is absolutely distinguished. Amongst those are the Anselm Payne Award, which is the highest recognition in the area of cellulose and renewable materials. He is also a fellow of the American Chemical Society, the Finnish Academy of Science and Letters, and the recipient of the TAPPI Nanotechnology Award. He is an adjunct professor in the Department of Chemical and Biomolecular Engineering at North Carolina State University in the US. He has also other appointments which are honorary in nature in Europe, in Finland, Sweden, and in many other places. Dr. Rojas is a member of the Marcus Wallenberg Foundation Selection Committee and the TAPPI International Research Management Committee. So without further ado, it's with great pleasure that I introduce you Orlando Rojas for our first keynote speaker. Thank you and welcome, Orlando.
Thank you so much, Federica. Very nice and kind of you for inviting me to join this very great seminar series, workshops that Genome BC has organized. This is really very timely, and I congratulate you and your team for arranging this event. It's really quite important for us to look into the genomic aspect of the work that we develop. I will be talking a little bit about enabling technologies for bioproduct development, and I hope that maybe you can capture some of the ideas that are really important for translating what we investigate at the bench scale so that we can translate the knowledge to producing a bigger impact. So my talk will be surrounded this topic, but maybe very briefly, just to introduce you to the Bioproducts Institute here in University of British Columbia. It was already said that this is a large ecosystem of researchers working in the area of bioproduct development. And just want to mention how we are integrated to advance our mission. As you can see in those circles that are in the center of the slide, we are organizing themes or trust areas. Going from left to right, we start with biocatalytic transformation and engineering of biomass. That's where genomics are very relevant. We have also bio-based polymers and carbon materials. These have become very relevant to today's technologies. Then we have nanotechnologies from biotic sources. And finally, the bigger picture, the more or less biorefinery systems, that is to use unit operations to carry out the transformations that are needed. But very important, since I joined UBC, I think we recognize the importance of having earlier assessment of the social, economic, environmental impacts. And for that reason, we have a team of professors and researchers working on those aspects so that we can also look into policy and regulatory aspects. So these are really very important components that I want to highlight to integrate the whole, let's say, value chain in the area of bioproducts. So when we think about what we are able to really produce or enable, we can take a look at our living environments. And that's what we did very early on with this image on the left. That's my apartment here in the university. And to look around, what are the things that we can produce from biological materials with keeping in mind the idea of achieving defossilization of our society. And pretty much everything that you see around can be made from biological materials, including, of course, plant and biomass residues, going from the windows all the way to the insulation materials, the textile materials, and many others. So I will be sharing a little bit about those subjects, keeping in mind that what we want to achieve here is to become a leader in the area with the objective to valorize fiber utilization and achieve a low carbon economy. And of course, also keeping an eye on the bioinnovation and adoption of what we produce in the labs. So in this area of bioproduct development, a word that has become very critical, and as you can see from recent policies, regulations, is circularity. Circularity now becomes so important in our business, recycling materials or extending the life of the materials that we use. And so in the context of the bioeconomy, we want to think about advancing a regenerative biosphere. This is the biology that surrounds us in the form of plants, agricultural residues, forests, combined with a circular technosphere. This is what we do in our businesses, in our technologies, to add value to those materials. And if we think about that circularity that we want to apply, I think there is no better example that looking into trees and plants in general. So I will refer to this circle that you see. That circle goes around years, up to from 0 to 500 years. And what I want to show here is that CO2 is being captured by plants in the process of biosynthesis using sunlight, CO2, and water. By the biosynthesis process, we obtain the cell wall of the plant of the biomass. And in the case of wood, trees in general, we can use them for construction, as is typically done since thousands of years ago. And then thinking about how the material from construction should be recycled, starting with that. And then that becomes a very large time circle, right? That spans the 300, the 500 years. That will be the lifespan of the materials for construction that are used for construction. But if we look into other streams that are rich in biological resources like agroforestry and biomass residues, we can think about a smaller time spans that need also to be circular. And that also applies to paper and textiles. And then eventually we will have residual materials that have little use as a structural component, but can be actually considered for the production of nanomaterials, lignin materials. We are going to talk about this. And then eventually anything that is left that has low value or is not able to be processed, then that will be the purge in the system. That will be the losses that will go to landfilling. But keeping in mind that here we have the huge advantage that the materials that we use are biodegradable. So you see this combination all together. This is the bioeconomy, in fact. And I want to bring up here what in 2009, the European Union decided as the key enabling technologies to advance the future bioeconomy. You can read on the left the idea of advanced manufacturing technologies and advanced materials, nanotechnologies, industrial biotechnologies. That's when genome, BC probably plays a very important role, as well as micro and nano electronics, and finally photonics. That chart was revised more recently, and then you can see the evolution where we are merging advanced materials with nanotechnologies and open a broader area that spans, in general, life science technologies to include industrial biotechnologies and synthetic biology, for instance. Then micro nano electronics are merged with photonics to open a space for the stream of artificial intelligence and digital security and connectivity. These are really critical areas. So I will be maybe expanding more in detail about these manufacturing technologies in the area of bioproduct development, and also connecting this with the integrated biorefineries. And on the other hand, of course, as far as the advanced materials and nanotechnology, I would like to mention smart sustainable materials in general, nanotechnologies, and the idea of producing lightweight materials. So that would be my main pitch. Keeping in mind that I'm not really working in the area of biology, I am surrounded by amazing people that are working in molecular biology, genomics, synthetic biology. What I do for the most part is in the area of material development using bio-based colloids. So more or less nanotechnology, colloid, and surface sciences. So going back to the circle, I want to introduce maybe the topical area that relates to construction that is so advanced, so important for the Canadian bioeconomy. This is already recognized as a very important component because it's very relevant in the preservation of CO2, the capture and storage of CO2. And if you are in the campus of UBC, you can appreciate this building that is made out of wood. At some point was the tallest wood building in the world. Now there are others, but this is really an excellent example of what we see now in the regulation in different countries about using wood as a construction material for the purpose of CO2 storage. So, but here we need to consider the circularity, and I bring this back again. And in that sense, at the end of life of these construction materials, we will have construction and demolition waste. And I will give you a single example about what is possible for us to do as a relevant area where we can utilize residual material from construction. This is something that cannot be undermined. For that purpose, of course, I should mention that we have other streams, as I have already mentioned, that have shorter time spans, but are equally important, and I will be referring to those, as I have already introduced to you. Anyhow, in the area of bioproducts, an area that has become very relevant around the world, especially also in Canada, is construction materials. And here there are many recent developments in the area of the smart biohomes. If we look at wood utilized in the living environments, you can appreciate that the advanced materials that are being, or the advanced designs that are being developed in different research labs around the world, including UBC, but of course there are many other, involve the construction materials where we can achieve control on the temperature. We can also have energy harvesting systems, air filtration systems, CO2 absorption, energy absorption, and light management. There is a lot that is going on here, and many of these demonstrations are placed in living labs in many universities around the world, and many of those are also transitioning to real life. So it's very important. But once again, what do we do with those materials? And this brings the topic of the construction and demolition waste, C&D waste. Here I want to acknowledge the fact that if we look only in the American ecosystem, the American municipal wood waste is really generated in a very large volume over the years, and it's increasing with time. So if we look at this chart on the left, we look into the materials that is generated and how much of those are recycled. And it's very little, actually. So this is really a great opportunity that is very important, especially in urban centers like the city of Vancouver and many, many others. And here we have a little incursion that I will show in the next 2 slides about what is possible in this area if we use the technologies that I have mentioned before. You can find more details in the paper in the bottom. But essentially, what we have here is really a great opportunity to use urban waste in the form of construction and demolition waste. That is very important. You see the numbers in the city of Vancouver alone, also in the bottom. The idea here is to look into advanced technologies where we take all these fractionated biomass, split biomass from demolition, but can also be extended, as you can appreciate on the top left, to decayed wood or even sawdust. In general, any residual biomass material can be put back together into structures by using the power of surface chemistry. But here I should also include the power of biocatalytic transformations. But in the simplest form, if we take those pieces of wood, we can do or apply delignification to remove the glue that holds together the fibers in the construction material. That will be lignin. We do delignification. Then we apply partial dissolution of the other component in wood that's called cellulose. And then that dissolution that happens at the interface, you can appreciate this on the green areas of the biomass, that can be then regenerated in an anti-solvent, similar to what we do in the production of cellulose-based textiles, and then coalesce, solidify the interface in such a way that we have like a gluing or adhesion phenomena going on. And that will be at the interface. So essentially, this is adhering the components that are split back together in a way of healing the material, applying topochemistry. And here topo refers to the general idea that we apply this not to the body of the material, but to the interfaces, those areas that are exposed to the neighboring material, so that we can group them back together in a process that we can think about as a healing. What is relevant here, and is a beautiful example in the bioeconomy of upcycling, is that those materials that are obtained have been proven to be stronger than the initial material that was used at the beginning. That if you compare, for instance, here the specific strength for different materials at the end, the healed wood that I just described, you can appreciate that strength is higher than densified wood and the natural wood that was initially used. And also competitive in terms of the specific strength with metal materials. Main point is that as far as construction materials, it's a great possibility to replace the current elements by biological materials. And here the power of biology, the power of surfaces, colloid sciences, chemistry, and material science is really very relevant. I want to give another example that is very recent. You can see in the bottom the publication and find a bit more details. But this relates to carbonization. And this, of course, is very important if we think about forest fires, but also recent technologies that are looking into carbon materials, not only for batteries, but for many other energy, so-called energy materials for energy harvesting. The angle that we play here along those technologies is to use wood, as you see on the top left, to do like we did before, partial delignification. So we remove part of the molecules that exist in the cell wall of the wood. And then we apply carbonization at a high temperature. Here, interestingly, that happens at a high temperature. Lower temperatures is not going to work. And then what we obtain is, as you would expect, a carbon material. That would be the black wood. But what is interesting here is that we use the biological structure that is already in place in the form of the cell wall of the fibers, the microfibrillar structures based on cellulose that exist, again, in the cell wall of the fibers, to unravel and expose those fibrils in the way that you see in the cross-section image that is shown in the bottom. This can be considered as vertical aligned carbon, micro, and nanofiber arrays that are actually advanced materials in many technologies. I can give an example of this in the next slide. But before going there, you can already imagine that this sort of micro arrays of fibers can be very interesting, especially because of the color, the carbon material, to trap light. And the same way that we have talked about building windows with wood, that's the so-called transparent wood, that is already a technology that is quite advanced. Here we go to the opposite direction, using wood to produce an opaque, light-absorbing material. That's what we have here. And what you can see on the left, bottom left, is how irradiation, light, sunlight, will be trapped by multiple reflection, and that means that the material becomes anti-reflective. In the center, you will see how we talk about wood carbons and what the total reflectance in percent is versus the wavelength of the irradiation light, and how the super black wood that I've just explained really reduces tremendously the total reflectance of the material. So this is an anti-reflective material. Similar materials like this have been designed and created. An example is the so-called Vanta black. You can see that in the news. Essentially, it's a material that you can put on top of given designs, like in this case, this bust. And if the Vanta black that is produced with carbon nanotubes is placed as a coating, you can appreciate that there is no light reflection. Therefore, you cannot see the shades of the material. This is very important in military defense aspects as well as many others. It's an advanced material already in commercially available, again, called Vanta. But it's a material that requires a huge investment in the way of producing the carbon arrays by using clean rooms and very expensive tools. And what we're doing here is bypassing all these very expensive processes and expensive materials using just wood that is given to us by nature. Using the biology that is given by nature, we create a competitive material that has a very good anti-reflective properties similar to that of Vanta black, the one that I'm showing on the left. What to do with this? There are many examples that I can share with you in the paper. You can find more details, but this is important in laser beam stoppers. It's important in telescopes designs, advanced materials, as well as I said before, in defense and military purposes. But one that is a bit closer to us is energy conversion. That means sunlight to thermal energy conversion and including desalination. Taking this type of wood with a super absorbent on top, anti-reflective, means that we can locally heat the material by sunlight, and in that way then convert sunlight to energy. And if we place this in connection to seawater, then evaporation will happen, and we have also desalination. And you can see some metrics in the bottom. So simple technologies that we can classify as nanotechnologies that are very useful in terms of energy. Okay, that was the case of using wood materials. I place two examples to trigger a little bit of thoughts and the importance of considering wood for construction and advanced nanotechnologies to take advantage of those materials and prolong the lifespan that they present to us. The other component is that I promised to share with you is agroforestry residues. Very important for the province, very important in the future circular bioeconomy. And as I have explained, we're dealing here with a shorter lifespans or service life of those materials, but are equally important. And what we want is to create those circles in all the materials that we use in society. So in this example, I will take the case of the residues from the production of blueberries. This is a collaboration that we have with Chile, but berries are important to Canada, Nordic countries. Point here is that there is a lot of biomass that is generated, that is not utilized, that is left. Think about just pruning operations and many operations in the process of optimizing the growth of the plant. And then we have that biomass. But you can extend this to many other platforms. You can think about wheat straw, hemp fibers, and many other streams. But in this case, I just take an industrial blueberry waste. And in this case, we can use the material to create platforms. On the very top right, we talk about a biorefinery platform where critical chemicals, platform chemicals are produced. That includes polyphenols, sugar fractions, and many others. I will skip those for the time being because there's really a lot that we can discuss there. But I will refer maybe to something that is of practical relevance nowadays, and that will be to take that biomass and find a solvent, in this case, looking into green solvents that can dissolve the material in such a way that we can process them by using different operations, right? So here we consider ionic liquids. Ionic liquids, of course, have been around since many years back. But nowadays, we know there are new generation ionic liquids that I will mention again in other slides that are very interesting because they are low cost, environmentally friendly, and can be recycled. And that's what we use here. We take those ionic liquids to dissolve the whole biomass into dope that can be used, for instance, for 3D printing and functional textiles. I will reach the example of filament production in the next slides. But that's the idea. So what you see here is how the whole biomass is dissolved, a dope, a solution is produced. That solution that takes the whole biomass is then extruded into a coagulation bath. That coagulation bath in this example in the video is just water in the trough that you see there. And then a filament is produced. Here, as you see the slides and the video, that's what we're doing. It's a process that is called wet spinning. In some other cases, we talk about air gap wet spinning. It's very typical of textile technologies. But the beauty here is that a filament is being produced, and that filament can be considered for textiles. That filament that you observe is brownish, and this is because we're using the whole biomass. And this is very important because now we're looking into universal solvents that can really be agnostic to type. It can dissolve the biomass, and that includes, in this case, the whole residues from blueberry plantations, and then produce a filament that you see on the right. Those filaments, of course, have very interesting properties, and I want to bring here, the power of given biomolecules that already exist. Let me see, okay. And that will be the case of this experiment that we carry out in the coast of Cozumel with a collaborator, where those filaments were used to attach the supporting materials for coral reef restoration. And this is just here, or I bring in this here just as an example how those filaments that are made from cellulosic streams mainly acquire water resistance. So in the ocean, it can stand for a long time to be used as a textile or a filament material. The reason for the water resistance is not because cellulose, but the presence of biomolecules like polyphenolic compounds that bring those properties to the system. So very interesting. You can expand with your imagination what is possible. So that's a couple of examples of agricultural waste. We can expand and can share with you many others that are going on. Let me talk about paper and textile circularity. paper circularity is well demonstrated. The recycling rates of paper are around 70, 80%, depending on the jurisdiction. This is a great example of what is possible to do with forest and biomass materials, fibers, including residual biomass from agricultural production units, paper. In contrast with plastics, where we talk about 2% of recycling rate, here there is a really great opportunity. That's why nowadays we're talking a lot about paperization of society, the use or the adoption of paper in new generation packaging materials. And I can relate to you many opportunities that are coming from consumer products companies that are looking into the use of paper-like materials to substitute plastics. In the context of textiles, clearly there is a mandate for our textiles, the textiles that we wear, to be produced from recycled streams. And large companies around the planet are already advancing their mission about using 100% of recycled textiles in the production of textiles. Great opportunity for biology transformation, as well as other chemical and thermomechanical platforms. Anyway, going back to the ionic liquids, this is a great advance that I want to bring back in the context of textile recycling, as well as paper recycling. Is the idea of green solvents, the so-called protic ionic liquids. Examples are shown here that can be used to dissolve biomass to produce the dope as the one that I had explained earlier. The beauty of these ionic liquids is that we can dissolve the material, we do the spinning as I explained, and the materials can be then produced while the solvent can be recirculated. And an interesting example here is actually using cardboard, waste cardboard, like the one that you see on the top, to produce textile fibers that are converted then to the actual garments. This is well shown, well demonstrated, and my colleague Herbert Sixta in Aalto University in Finland is pioneering this type of technologies. There is a startup in the area, and in general, in our ecosystem, there are many companies looking into these opportunities for generating textile from recycled or low-value materials. Something that is closer to home is one experience that we had with that was during the pandemic, actually, with the lead designer for a company called Vera Wang. It's a high fashion textiles, and she looked into how the production of textiles takes so much energy inputs, material inputs, really very large carbon footprint. If you think the use of fibers, that can be cotton fibers or other types of fibers, yarn spinning, fabric weaving, dyeing, and all these operations that happen in general in many different countries, in fact, right? So if you think about the materials that we wear, they have a history and they have a huge carbon footprint. And the idea that she had, that she presented to us, what if we can use cellulosic fibers like the one that we use in paper for a direct manufacturing process to produce a textile material? That speaks to the advanced processing technologies that I mentioned as one of the pillars of the advanced technologies to advance the bioeconomy. And here what we did is something similar to what I presented earlier in the case of wood recycling. We took a solvent to partially dissolve the material. We use given techniques to make paper-like materials, but with very good control on the fiber deposition. So we skip weaving. What we have is a paper-like material, and that paper-like material become super strong, leather-like, water resistance, to the point that in making prototypes, this shoe top was created. And here we have a material that uses actually 3D printed molds to make the shapes of the objects, in this case, the shoe top. And then by applying the magic of the technologies, nanotechnologies that we use in the labs, then it was possible to produce a garment, a shoe top that you can put back in the washing machine and can be washed. It's resistant to water. Very interesting technology that startup now moved to North Carolina in the US and is now scaling up the production of these solutions that really can be very disruptive. One interesting thing that I want to share with you as well is how these technologies can be also used in combination with CO2 capture. And this is very technical, but I hope that I can explain this in the simplest possible way. We have been talking about dissolving lignocellulose materials, in general, biomass. What if we take cellulose, the cellulose that we find in cotton, the cellulose that we find in tree fibers or wheat straw fibers, and etc., and we use the simplest of the solvents, shifting from a uniliquid to an alkali sodium hydroxide solution? What you will see is that if we measure the viscosity of that dissolution of cellulose, that viscosity is actually pretty low, which is good because then we can extrude the material in the process of filament spinning, like the one that I showed earlier. In other words, if we take a fresh dissolution of cellulose, what you see on the right, and we invert the container, that will flow. That's an example of a very simple way to say it's a low viscosity dope, low viscosity dissolution that will flow easily. But notice that we talk here about airtight material that was tested after 1 week. It flows very easily, but it requires for the material or the solution to be airtight. If you expose the material to air, as usually is the case, what is going to happen is that the viscosity will be increased tremendously. That's what you see on the left. And then when you invert the material exposed to air, then the material will form a gel, a hydrogel in this case, and doesn't flow. That's bad because that means that we cannot use high concentration dopes in the production of textiles. And there are a number of problems that emerge when the material becomes so viscous and jellified. So obviously, this in a way lead to the very simple idea that if we process cellulose dissolution in the absence of CO2, that is in airtight environments, we can do textiles, we can do filament spinning, and we can also carry out 3D printing operations. That's what you see in this quadrant that I show for high cellulose dopes in airtight atmospheres. That's what you see in the bottom right. But if we turn things around and think about the same material absorbing CO2 from the atmosphere, so promoting that CO2 absorption, then we have mineralization. And what we found is that the cellulose that is dissolved, that is in the dope, combined with the CO2 and the ions that exist in the solution, they will form different mineral species. And those mineral species are shown here on the left as particles that then become components that are very interesting for construction materials. So we tested this for ceramic glazes. We tested this for concrete. And what we found is that the cellulose that is present in the dope will contribute tremendously to the robustness of the material. Higher strength material, lower weight, excuse me. So very, very interesting. And what we're doing now is to play with those concepts using a wet spinning unit. And this is where, the different resources and infrastructure is needed for us to test this idea. So in the BPI, we have a number of units like this one, wet spinning, that we can use to very systematically analyze the formation of filaments and, converting the dope from biomass. By the way, that includes cellulose, as I have explained before, but we're very active working with ocean biomass like chitin sources to do the same type of filaments in this process that I show in this slide. At the end of the day, a filament is produced, in this case from dopes coming from sodium hydroxide dissolution. And if we look and compare these materials with different type of filament from different processes, rayon, nylon, polyethylene filaments, and others, you can see in this plot of a specific strength versus a specific Young modulus, that is the strength versus, let's say, the stiffness of the material. Our materials that you see there on red are extremely competitive. You can find details in the literature, but yeah, I think this summarizes a little bit opportunities in these areas. Of course, there is much more that I can share, but I think this is a very good example of what I wanted to say. Okay, so we took a look into forest, agroforestry, as well as construction materials, how to make them circular. Let me talk about then what is left, or the residues that can be valorized in other ways. That will include what we call in nanocellulose and lignin streams, as well as other molecules that we find in plants. I think this is one of our favorite areas of research, and I can share you some examples, actually closer to the biology that we discussed during these 2 days, that is so important as an arm to develop this material. So what you see on the right is the case of fibrillated cellulose. Canada is very strong in this area. There are really important announcements about the production of cellulose filaments by a company called Performance Biofilaments to produce in large scale these fibrillated cellulose that you see on top. Large fibrils based on cellulose. There is also another component of these nanotechnologies, again, going back to the enabling technologies for the future bioeconomy. We mentioned nanotechnology. Here we have nanotechnology of forest products and plants in the bottom of cellulose nanocrystals, another way to present this type of materials with very interesting properties if we think about the merits of using nanomaterials and nanotechnologies. So the main proposition here is very simple. Speaking, in a very high level, you can read details about the technology in the bottom paper that is cited. That's in Nature, where we show how the transition from these fiber structures can be very important in developing next generation nanotechnologies. And this is now coming into realization in many places around the world and in many areas of technology. So in blue, you can see the idea of deconstructing the biomass. We start with, on top, cellulosic fibers, plant fibers. As you know, they are hollow. They are made from a cell wall that is very interesting, very well structured. It's structured in form of microfibers, microfibrils, and elementary fibrils. And eventually, if we think of the main building block, that would be cellulose chains. Of course, these materials are very difficult, as I have explained before, to dissolve. So reaching the cellulose molecular dissolution is hard. You need to have special solvents, like ionic liquids that I introduced earlier. But using enzymes, of course, there are very interesting routes to dissolve or modify, functionalize those different types of cellulose in different structures. What is the value that is proposed here? Well, as we do deconstruction, as we reduce the size of those materials by enzymatic, mechanical, thermal, and chemical treatments, we generate value. And that's what you see in the red arrow. The idea here is pretty much enclosing the idea of nanotechnologies to generate value and performance. There is a cost, but to a large extent, the performance overweights the cost and makes the system quite attractive for many applications, including composite materials, advanced materials, and others. One that is interesting relates to, again, going back to cellulose. And I want to ask here, if you see this image, we have different sources that are familiar to you. And I asked the audience, which of those are sources of cellulose? And you can have a few seconds to observe. Of course, trees, blueberry biomass that we mentioned. But about here, what are those that are able to produce or contain cellulose? Maybe you can test yourselves. Well, the answer is here. There are things that are unexpected. Not only saguaro, but in marine animals like tunicate. These are important species that we find in the ocean. Really major problem in the East Coast because these are organisms that adhere to surfaces and create a series of problems in an invasive species. Tunicate contains very pure cellulose in the structure. It's a source of cellulose. We have green algae from ocean, of course, and different type of plants. The one that we're working with all of those, but the one that I want to comment on is the one that is produced by bacteria. That would be the frame number D. bacterial cellulose or bacterial producing cellulose. And what we have here is a construct, in this case, for instance, the acetic acid bacterium, that, as you may know, forms a biofilm, and that biofilm is no more than cellulose biofilms. Why the bacteria does that is, in a way to protect from UV light, protect from antibiotics and physical disturbances. It's a way how biology works in such a way that the bacterium builds an environment to protect the microorganisms, and is a process that is an aerobic process. And this is how it looks. What you see on the right is the bacteria spread around, those more or less cylindrical features that you see. And it's immersed in a biofilm that is fibrillated cellulose, the same cellulose that we find in plants, the same cellulose that I talked in the earlier slides when I talk about nanofibrillated cellulose. So this is a very interesting material because it forms a woven network of pure cellulose nanofibers. And we have worked since a long time ago, I would say maybe more than 15 years ago, with our colleagues in Colombia, who discovered in the fruit market in Medellin this strain of bacteria called Comagotibacter medellinensis. Medellinensis is because of the city of Medellin. But like this, there are many other strains. And this we found as be very interesting strain because it really produces cellulose in high yields at a low pH. Think about how this bacteria survives in very acidic environments like pineapple juices, right? So bacterial cellulose is produced, that's what you see, and that bacterial cellulose forms a pellicle that you can separate from the culture medium, and after removing the protein makes a film that is very strong. You can see that here. And our students are looking into uses of these biofilms of cellulose. Beautiful examples. I have colleagues in Imperial College that are using bacterial cellulose combined with polymers to produce bulletproof armors and windows for military purposes, right? The same that you see here, we're using this to create corneal replacements. And I can give a number of other examples of how these materials can be used. From the most obvious way, artists and designers already captured this idea. And what you see here is an example of the bacterial cellulose that I already showed as a way to produce a leather-like material. This is very relevant. And if you Google bacterial cellulose for textile materials, there are plenty of examples. So it's a beautiful of what can be done. What is that maybe prevents a wider adoption of bacterial cellulose? We can talk a little bit about that. But there is here an obvious advantages of using this microorganism-generated cellulose over those that are produced from plants. You can read on the left the main properties. One of those is the molecular weight, the dP of the cellulose that is produced by bacteria is very high. It's highly crystalline and is very stable, and of course then has also very high strength, and is produced really by very little energy. The question is, of course, how to put those fibrillar cellulose into organizations and structures that can have a use, and I mentioned a couple. What are the disadvantages? Well, it is, of course, more expensive than using just the trees and plant biomass to isolate cellulose. And there is not really currently infrastructure in place to produce this in large scale, even though I would say in some places like in Germany, and I know in Brazil and in China, there is a lot of activity in the area of bacterial cellulose. Anyway, we need to look into value-added materials, and I think the best example and use of those bacterial cellulose is in biomedical applications, is, added value materials. In many applications, we will need to have a modification of the cellulose that is produced to make it bioactive, to make it conductive, to change the color. There are many things that we can do, and this is very easily and actually quite nice to do in vivo in the fermentation process by adding the given additive to the culture medium. That's possible. We have the additive with the microorganism, grows a pellicle, and that pellicle can bring that additive that we added. It can also be done ex vivo. That is, we produce the pellicle and then we make the modification or add the component that we want to add, right? So that's a treatment that can be applied. We're working in this area because here synthetic biology can be, as you can imagine, very important in the transformation of the process, modification and functionalization of the cellulose that is produced by the microorganisms. Anyway, examples, we can produce this both in vivo and ex vivo to make the pellicle or the biofilm antimicrobial, conductive, or to enhance the strength. So really great opportunities in these areas, I would say. So there is a lot to be said here, and the research is already there. There is nothing new about the production of bacterial cellulose. In fact, if you go to the Asian market, you will find nata de coco as an example of bacterial cellulose that we eat. But what is needed here, of course, to use the power of synthetic biology, polymer science, and bioprocessing to produce economically viable bacterial cellulose products. And I think there is a huge opportunity in this area. Since I mentioned that biomedical materials are relevant to this system and products, and with the idea of having value-added utilization of this type of biofilms in such a way that we justify the use of the material, let's take a look at some advances that we have done in the area of biofabrication. We call this biofabrication of cellulose films and structures. So, obviously, as you can imagine, if we take a mold, like a PLA mold or any mold, we can grow the bacteria in such a way that we can create face masks. This is no surprise. This is already in the market. If you go to Japan, in Korea, this is very typical in those markets. But what we advance here is a very interesting way for biofabrication in such a way that we guide the bacteria to make structures in 3 dimensions. That's in the bottom reference by Greca, 2018 in Materials Horizons, where we created this sort of scaffolds with the shape of an ear by a very simple biofabrication process using the bacteria. So as you can imagine here, of course, medical materials are very relevant. Likewise, we can make this into tubes and many different structures. One that was quite nice to see is to grow the biofilm with bacterial cellulose into structures that we can design as meshes in this case. And the idea here was to produce structures that can be used in the body as a biomedical material. So that's an example of our student creating the biofilm with cellulose with given designs. More closely, we can see here an example, and the beauty here is that these structures are auxectic. These are auxectic meshes. What that means is that if we make the biofilm with those shapes, when we stretch the material in one direction, rather than becoming narrower in the perpendicular direction, actually expands. And that's very important for comfort, for body comfort. If we put this on the elbow or in any body part, it's important that we prevent the shrinkage of the material in the lateral direction opposite to the stress direction. And that's what is called negative Poisson material or auxectic materials. Very important, very relevant in the industry, in textiles and other applications. Anyhow, those textiles, or those meshes rather, produced from bacterial cellulose, were used to treat in vivo hernia as a hernia repair, and that was tested actually in small animals. And what we observe is very interesting opportunity. The established materials for this purpose are on the right. These are based on polypropylene meshes that are being banned because it creates a lot of problems in the body, erosion and discomfort, and a number of other issues in the body, in the human body. But using the biocompatible material that I have introduced so far, cellulose, in the form of those meshes, really can have very good response as far as foreign body reaction, granulation tissue, and scar tissue really great material. It's an example of a high value adoption of bacterial cellulose for that purpose. Where are we now? What we're doing now is to do this really in 3 dimensions. Here you can see some work where, using techniques like the ones that I showed earlier, we can extrude bacteria in a given container and form materials in 3 dimensions that are mimicking, as you see on the top right, that mimic, for instance, fractal structures similar to vessel elements and other elements. So great opportunities in this area. That can be done with different shapes and forms. In a nutshell, what we do is we guide the locomotion of the bacteria so that we make the bacteria to go where we want to go and make 3D structures that are made by design. One further development that we published this year, actually, this is already accepted in the bottom, is to use not only culture medium, that is aqueous solution, air interface in the aerobic process. Now we know how to do this at the oil-water interface, meaning that the bacteria will grow the biofilm in the absence of environmental air that is needed. This is under the hypothesis that different oils dissolve oxygen from the atmosphere, and that oxygen or air is enough for the bacteria to grow. So we can do under liquid fabrication or under liquid biofabrication as an example of this area of biology. What I'm talking here is, goes beyond these laboratory exercises. I bring the case of Modern Synthesis Company. It's a startup in London coming out from Imperial College. I'm a part of the scientific board of this company, and this has become very popular. If you Google them in internet, you will see beautiful developments where bacterial cellulose is used to produce the shoot tops similar to the one that I showed earlier, but in this case, using bacterial cellulose. And like this, there are many examples that I know closely in, for instance, in Chile, in UK, in Finland, and other places. Of course, Canada. Here we are doing our own share. So this is all that I wanted to talk about bacterial cellulose. The material is there, biofabrication method is there. Even the infrastructure is also easy to secure, but we need to advance more. I think this area that is very important for many reasons that you can guess. And one of those is that the agricultural waste can also be used for that purpose. So I know a company in Portugal that is looking into the use of sugar streams to grow bacteria and produce these bacterial cellulose biofilms that I have explained. There, in a pulp mill, in a forest products company that processes forest biomass, there is a lot of sugar that can be used for this purpose as a culture medium. So there is a potential here for different waste feedstocks that can be used. You can see or read those in the bottom. And great opportunities for making leather-like and other materials that have a mission as far as carbon replacement, fossil carbon replacement, or the defossilization. I think I'm running out of time, and I want to give time for questions and answers. In the next slides, I will just tell you what I plan to talk about, but then we shift to questions so that there is an opportunity for questions and answers. But maybe if you allow me, in 5 minutes, I want to talk about other material that is important in plants, all plants, and that will be tannins. Tannins is what we call the Swiss Army knife, multi-purpose. Tannins contain a structure, as a molecular structure, that is engaged in different interactions, hydrophobic interactions, electrostatic interactions, pi-pi stacking, an amazing molecule that we can use not only as an antioxidant, or the tannins for the leather industry, or those in wineries, but actually to create solutions to obtain cleaner air, cleaner water. What you see around the Swiss Army knife that we call tannins, a polyphenolic compound, around that, I am placing different molecules that are typical of antibiotics. And you may know that antibiotics is a huge problem in our water streams, poultry farms and other livestock production units dump in the water a lot of these different antibiotics for the given reasons. These are difficult to detect and are creating great problems in our ecosystems. So what we propose here is actually use tannins to remove those antibiotics. And we tested this in poultry farms. And the concept is very simple. We took the typical filtration units that are used for filtering water, but we coated them with tannins, and then we achieved very high antibiotic removal that was really very universal to all the antibiotics that I show. I will skip the next slide because of time. I give a little bit more details about those, but it's really an awesome opportunity. That's in a nutshell what I wanted to share about this. The second example that is very recent and attracted a lot of attention here in Vancouver is the issue of microplastics. Everybody knows about microplastics. I don't introduce the topic. The issue here is that taking the same advantage of the multi-functionality and the way that the tannins in plants interact with different structures, we can test those for the nano and microplastic removal. That's what we did. We extracted tannins from red cedar bark. That's what you see on the left. We place those tannins, it's a polyphenolic compound. We absorb them on wood waste, sawdust, the one on the right. And then we put this in a separation column, like the one that you see on the far right of this slide. And then we pass through the different aqueous suspensions containing different microplastics. And what we observed was a very high capacity for these materials to bind, absorb, and remove those microplastics very quickly. Here you can appreciate the case of microplastics derived from polyester, from textiles, 99% removal rate. Those from polyethylene, from the grocery bags that we use, 95% removal rate. Polystyrene from the coffee cups, 99.9% removal. Then looking into other type of plastic-like material like polypropylene from our Tupperware, 99.3% removal. PMMA, a little bit more fancy, but 96%. In general, you see my point, at least 95% removal rate of these nanoplastics. And very simple technology. Here is just simply using tannins, a compound that is given to us by nature to produce these technologies that can be scalable, actually, to make a better, cleaner water. Anyway, I think this is the end. I want to tell a little bit about what are the challenges that I see important in the area. And here, UBC can be really instrumental. One, in the use of natural materials is the diversity of building blocks, the need for fractionation and integration technologies. That's what I show on the left. Also, very important, we need to look more and more into the full use of the resources. So access to the resources is relevant. The problem here is that most of the waste is dispersed, is distributed in the geographical sense, and that's a major issue. That calls for the integration of smaller units, local units, to process these residues and this waste. Understanding water interactions and drying is critical. There is a lot there to be said about this, because the typical fossil carbon processing use heat as a medium for transformation. When we talk about biological materials, we use water, and still there is a lot to be said about interaction between water and these materials. And finally, this is important, the use of the power of biology to advance those aspects. I think I better stop here to give room for questions, and just to acknowledge my group. They are the ones doing the work that I presented. I only show my own research, but now multiply that by 60. That's the research by the whole ecosystem in the Bioproducts Institute. With that, I finish, and hopefully we have still some time for questions.
Orlando, thank you so much for this wonderful presentation. Yes, we have time for questions. And I just want to say this was incredibly fascinating. And yes, you did mention quickly at the end the opportunity for GenomeBC, but as a genomicist myself, I see that you made such a perfect link from our need to continue to characterize biodiversity, at the molecular level, because it is so important for the work that you are doing, as you have demonstrated with some of the incredible examples you've given us. And then you made another, another comment that was made yesterday by our keynote as well, although we were talking about genome engineering technologies for health. But essentially that comment was, we still our knowledge of biology is limited. In his case, it was our knowledge of human biology, and I think in your case, it's our knowledge of the nature's biology that is very limited. Anyway, I'll move on to questions. You have quite a few, but thank you so much. So, what is the longevity of these bioproducts? Do they last as long as traditional building materials?
Well, I have a slide for that actually, but there was a recent report about some wood for construction that was found in Tanzania that was discovered in the mud and was dated to 500,000 years back, challenging what we know about archaeology and the materials for construction. So my short answer, wood-based materials can last for very long, as much as 500,000 years. I can give you the exact number if I find the quote. I would be happy to share it. But this is amazing. So, given the right conditions, in this case, an environment that was able to preserve the wood material, it was discovered that wood for construction was used dating back to so far back. So wood in principle can be used for very longevity materials. Think about the pagodas in Japan, constructions in China. They are very, very aged, they're very old, and they are still standing. So I think there is an opportunity there. But as I mentioned, still, if the lifespan is shorter, we still can recycle it and make it better. So that's very interesting. That's where we are heading to.
Another important question that we have from the audience is, what is the environmental impact of upcycling wood? So to this, what resources are needed, CO2 production, or anything that you can offer?
That's absolutely relevant question, and that would be one priority for what we do. So I give the case of ionic liquids. I put that because of that reason. Ionic liquids have been around, but there are a lot of evolutions and there are new systems that can be recycled. That has been one major issue. Green ionic liquids that can be recycled. If you think about it, these are very powerful green solutions or solvents that can be used in processing biomass. There is very little that is produced as far as CO2. Of course, you need to look back at how the ionic liquids are produced. Definitely there will be processes that we need to take into account. And this is what really matters when it comes to looking into life cycle assessment and those tools that I introduced in my second slide, where we really need to take a view about that. And we're very active in that area, but there is a lot to be done because we need to look at this into a very holistic way. It's not the material itself, but how it was produced. And absolutely, we need to account into the energy and material use that is implemented in those processes. One important point is use of water. Water is very important for us, and therefore now we have pushing a lot of the limits in processing. For instance, dry state processing, sonochemical processes, and enzymatic processes where the use of water is minimized.
Thank you very much. And then there's another question that I'm also quite interested in, and that is, are there any economic incentives or business models that will promote the sustainable management of agricultural biowaste that locally, nationally, internationally, that we could,
there is a huge appetite in the area. There is really a lot of interest. We have a partnership with North Carolina, the Sustainable Alternative Fibers Initiative, that is looking into this very nice ecosystem where they are looking different agricultural streams, miscanthus, sugarcane, hemp, wheat straw, and others that I miss, to look into how to process this for making packaging materials, textile materials, And I don't remember the third one, tissue paper, actually, that, whose production and demand is just growing. And huge interest in this area by many startups, many companies. There is an appetite. Here, the government plays a very important role as far as regulation, and many things won't happen unless the government has an intervention. That's critical. Moreover, I noticed that in the Canadian context that there is a huge interest in critical minerals, artificial intelligence, quantum matter, and also biomanufacturing, all very important, but we need really a Canadian strategy for forest and agricultural technologies. We are very far and getting behind other countries in this area.
Yes. Yeah, we have a tendency to go after the buzzword. Absolutely. I think you're absolutely right. So there is an interesting question, and that is quite specific, but I do want to ask it. What are the system requirements for and outputs for using tannins to break down microplastics?
What is the system? What the first part of the question?
Requirements. System requirements for breaking down.
Yeah. So this is one of the challenges, right? In natural materials, tannins is not a singular word, it's a plural. There are many types of tannins depending on the origin, biological origins, right? And here we have a debate to use pure streams of tannins or mixtures of tannins. And I'm more fan of the second one. Great opportunities to use the materials given to us locally by the resource that is available locally with little fractionation. But of course, the performance will vary depending on the exact composition of the material. So in general, a barrier is the variety of chemical, biological profiles of natural materials, as opposed to fossil materials that are so well established and so uniform. That's a huge challenge, and that calls for fractionation techniques and advanced processing techniques. But in general, I wish, or I think that would be where probably there is an opportunity. We can use the material as is with little fractionation and deconstruction. That would be the ideal scenario. But this is a very important point.
Okay, I'm going to ask one last question then to just say something. Orlando, you have a fantastic experience also abroad and internationally, and you bring that wealth of knowledge and perspective to us in British Columbia. But you are here, and the Bioproduct Institute is here. What can you say about the way that you see this industry evolving here in British Columbia? What is your interaction from the Bioproduct Institute with the industry at the moment? What is the landscape there?
So we have an alliance with the local forest companies. It's great because they bring knowledge, really great experience. They are not in that position to fund projects and to work with us, but they are really very engaged with the Bioproducts Institute, advising and giving us very important feedback. On the other end of the spectrum, that's where we see a lot of pull from the technology point of view. Consumer companies, I won't name any company, but many are knocking our doors because they want to work on the replacement of plastics for liquid packaging, flexible packaging using bio-based material. This is there already. There is a huge demand, but there is a gap in the technology. So big gap. Locally, the Ministry of Forest is really shifting the mentality, and recent years is really very keen about adding value and processing biomass in such a way that we produce more with less, that we use every molecule in a plant to produce value, and transition from the low volume production material. We're talking about timber, pellets that are always good, but going more into higher in the pyramid and produce materials that are producing lower volume, but with higher value. In that sense, I think the Ministry of Forest in BC is really very helpful and is integrating with us great opportunities. The final point is international. We need international partnerships. And the BPI is part of something that we call the Boreal Alliance with Switzerland, Finland, and Sweden. And we are really having an excellent experience building capacity, sharing infrastructure, and sharing talent. So mobilization of students. This is in the early stages, but points to what we are doing at present. Very important topic. And I always say global challenges need global partnerships. And here we need to integrate.
Thank you very much once again for this wonderful presentation. And we have a treat, which is that you will be part of our next panel, so we can continue to ask you some further insights. Thank you very much.